Okay, good morning, everyone. That's a bit loud. You can still hear me okay in the back? Okay. So good morning, everyone. I hope you've had a pleasant and enjoyable weekend. Got outside and got to enjoy the nice weather a little bit. Before we get started today, a couple announcements. So the second homework assignment is now past due. Hopefully you all turned it in. The third homework assignment on the data transmission unit that we started last time, we're going to continue today and we'll finish up on Wednesday, is also now posted. Remember, we have our quiz this Wednesday on the data storage unit. The quiz for the current unit, this data transmission, will be a week from Wednesday. So what I think is that the 11th. And just a note on that homework assignment, I put up the email. Both David and I are going to be out of the office the end of this week and part of the weekend, having very irregular access to email during that time. So the homework this data transmission homework would normally be due on Monday at 8:30, but because there's probably about a 4-day period where you're going to have a hard time getting responses out of us, I moved it to Tuesday. That way there's Monday. We both have office hours on Monday. We'll be back, and you can get your questions answered before the homework is due. So this one time it's due sort of a day later. That's why. Okay, and so on that note, just as a reminder, I posted an announcement to Blackboard, and I think I sent it out as an email. My office hours this week, again, have to be a little bit different because I won't be on campus on Friday. So I have my normal office hours this afternoon, and I have what would normally be my hour on Friday will be tomorrow at noon. So again, I apologize that this is 2 weeks in a row I've had to move my office hours. As far as I know, this is the last time this semester I should have to change those, at least in an expected way. And I thank you for your patience. Before we then dive in, does anybody have any questions about anything that was in the homework that was maybe due today, what we talked about last time? Okay. Then if not, let's jump back in. So what were we talking about last time? What did we spend most of our lecture doing besides having a pop quiz? Don't give me that look. There's not another one today. I say the word pop quiz, and I'm sort of like, oh, God. Yep.
We talked about data transmission, the loosely and looseless channels.
Right, so we were talking about data transmission, and in particular, how do we get information from one place to another? And we introduced a little bit of terminology. We played, remember, the telephone game at the beginning to see that, what are the different ways we can get information from a source to a destination. And we'd call any one of those paths, any sort of conduit for that, a channel. And we saw in particular that there were sort of two types of channels. There was this idea of a lossless channel, which says data always gets through with 100% accuracy and fidelity. But we could also have a lossy channel where there's always a probability that the information may not get through correctly. And this brought us to the issue of reliability. And so again, if you send a text message to your mom, how do you know she gets the right message? And so sort of the running example that we had, and we'll come back and we'll actually talk about where the answers to this question came from by the end of the lecture today, is think about taking your phone out, taking a picture, and you want to text that picture, I don't know, to your BFF. And so at least on my camera, or my phone, you get about a 3 megabyte picture. And assuming, if there was a 99.99% chance that every bit got transmitted correctly, what was the probability? And we discussed this last time. Should you bet money on this happening? No. In fact, you should bet every dollar you've got against it happening. That'd be a pretty safe bet. Because the chances of your friend getting 100% correctly, that is, every bit was received correctly, was about 10 to the minus 1,093. That is a very small number. Okay? And so what we were thinking about last time was, how do we deal with this amount of loss, with these errors that can creep in as we work with transmitting data through these now lossy channels? So again, to recap from last time, is there such thing as an actual lossless channel? No. It's a wonderful thing that exists in an electrical engineering textbook for a junior level course. It's not a real thing. Okay. So what are some different ways that we can try to cope with the fact that these channels are lossy? We discussed some last time. We can maybe resend the message. What we'll focus on, not today, but on Wednesday, is can we add either some redundancy or some extra data to our message that help us either detect, did an error occur? Because then we can at least say, well, if we don't detect the error, then maybe everything's fine and we can move on. If we did detect an error, send some feedback back to the sender to say, oh, there was an error, let's do something. Or could we also perhaps use the data in a smart way and not only be able to detect that an error occurred, but actually be able to correct for it without having to go back to the sender and say, resend that message? Okay? And so one of the examples of this type of code, again, the buzzword would be either an error detecting code or an error correcting code, was this idea of a phonetic alphabet that you've seen used on a bunch of TV shows and movies for a while. And anyway, so we'll come back to that next time. But what we're going to do, so our driving question is now, how do we know or guarantee that the messages we send are the messages that get received? Okay? Because we know there could be errors. And so we're basically going to take a two-step approach. Today's going to be point 1 on this list, and Wednesday will be point 2. Where today what we're going to do is look and see, how do we understand and appreciate how many errors might creep in during the transmission? Because if we know there's not going to maybe be that many errors, that might lead us to developing a particular solution strategy for how do we deal with the occasional error that creeps in. Versus, if we know that we should be expecting a large number of errors, might we want to take a different approach on the back end? Conceivably, yeah. Okay? And so today we're going to spend a little bit of time going into probability to determine what exactly is the impact of these lossy channels. Is this like a big problem we have to worry about, or is it something we can sort of sweep under the rug? Okay? And so this gets into a bit of a fun lecture from the history standpoint, because we're going to appeal to all of either our lesser angels or our greater demons today. And so does anybody know sort of what's the origin of probability theory? You've heard probability, so you flip a coin and what's the odds. Where did this come from? What was this originally developed for? None of these mathematical tools that we're discussing throughout this semester were developed because some crazy person had suddenly divine inspiration and said, I'm going to develop calculus. That never happened. There was always an application that led people to start thinking about these questions. What inspired probability? Does anybody have any ideas? Again, think of the hint. We're going to appeal to our lesser angels or our greater demons. Yep. Probably something to do with gambling or gaming. That is exactly correct. So back in, I believe it was the 17th century, when various games of chance were becoming available, I think roulette was what largely started this. And people were interested in trying to quantify what are the probabilities that I can win, or that I'm going to lose, or that it's going to be a push, or something like that. And they started developing mathematical tools to better understand either risk, how much, if I place the bet on this roulette wheel, how much risk am I exposing myself to? But then also to figure out what's the potential benefit or potential loss of that action. And so is this a profitable venture to understand these things? Yes. And how do you know it's profitable? Okay, because if you make the right bet, you win. That might be true, but there's a better way to show that this is profitable. Because casinos thrive. Because what they're doing is they're using probability theory to try to... Do the casinos really want you to win? No, not even remotely, because that's money they have to pay out. They let enough people win so that everyone comes in, but if you bet on any game at a casino, should you expect to hand them money or should you expect to get money? Should probably expect to hand them money every time you place a bet. On occasion, you might actually get some money. That's fine. But this is the idea of expected value, and we'll come back to that point. But anyway, so probability theory originally started with applications in gambling and to understand financial transactions and bets. Much more recently, it's had a lot more applications in sociology. Anybody think where gambling or where probability theory might be used in sociology? Who has a Facebook account? Who thinks it's too early on Monday morning to have to answer a question? Okay, all the other hands go up. Got it. Okay, have you ever you've seen the thing and they're like, here's someone you may know. And you've seen, and there's this whole list of people, and sometimes you have no idea who the person is. Other times you know them and think, I don't like that person, I'm not adding them as a friend. That's happened to everyone? Okay. But where is Facebook getting this? Well, they have this big set of sociological data, which is to say everything you post and do in Facebook and everything everyone in the world posts and does in Facebook. And it's using some algorithms to say, what's the probability that you know this other person? And I don't know what their cutoffs are. I don't know how the algorithm works. But it might say, well, there's a 90% chance you know this person, and so that pops up in that feed. And so they're using probability to recommend, here are maybe other people you might know, or here's a page you might like. Okay? Can you think of other websites that do similar things? Yep. Okay, LinkedIn might do a similar thing, and then you get, then of course you click the button and the person who you clicked it on gets a umpteen obnoxious emails at 3 in the morning for the next year and a half. Okay, so YouTube, like recommended videos. You can go in and sort of watch certain videos, and it's going to make recommendations to say, here's something else you may like. Exactly. Amazon, how so? Right, so based on the products you either buy or view, it recommends here's other things you might like. Interesting, when you start having either kids or young nieces and nephews, all of a sudden your feed gets filled with textbooks, teaching supplies, and books for 2-year-olds. Just if you're curious. What was that? Dating apps, absolutely, are going to try to make recommendations based on other information that you feed it. Instagram, absolutely. So the point is, in recent years, with all this social networking, probability has really started to become alive and well in sociology. And so there's a lot of neat applications. Finance. Where do you think probability might get used in finance? The stock market, like a hedge fund. Anybody know what the idea of a hedge fund is? So it's called a hedge fund because they invest in some things that they maybe don't think are going to do quite as well and some things they think are going to do really well to try to balance risk. So the idea of a hedge fund then is, you're not going to get, if the market on the average is maybe putting out 8%, on a hedge fund you might only get 3%. But if the market's going to fall out and suddenly the bottom falls out and the market's hemorrhaging 20%, on a hedge fund you might be limited at 5%. So it's sort of, you don't get as big of highs, but you don't get as low of lows. And how do they figure out what are those sort of expected barriers? Like how high can you go, how low can you go? They're using probability theory. Epidemiology. So what is epidemiology? Anybody know? Study of diseases. So how might probability be used to understand epidemiology? Okay, so what's the probability that the disease spreads? Has anybody played the game Pandemic or Pandemic Legacy? If not, you should. It's a great board game. The idea there, the probability that the disease spreads is basically always 1. That game screws you royally in this. If you haven't played it, you'd find out. But yeah, there's a bunch, like the Centers for Disease Control in Atlanta, spend a lot of time developing disease spread models to figure out when something like the Zika virus a few years ago starts to flare up. What are the chances it's going to spread? And can we understand what it's going to do to better than design how do we combat that? How do we develop quarantine zones and treatment protocols to try to get this epidemic contained as quickly and safely as possible with minimal exposure to the population as a whole? Okay? Can you think of other applications or other areas where probability is used? These are a couple that came to my mind. By no means is this list unique. Can you think of some others? Okay. No, keep thinking. If you think of some, let me know. Okay. So what is then the goal of probability? Not to understand if you go to a roulette wheel, what should you bet on? That's certainly an application of probability, but it's not the goal. The goal is to determine the relative likelihood that an event will occur relative to the likelihood of different alternatives. So think about flipping a coin. How many possible outcomes are there if I flip a coin? 2. Okay, so we're excluding the idea that the coin lands on its edge? Okay, I'm good with that. So there's 2 possible outcomes. Either we get a heads or we get a tails. So when we want to think about probability, what we're looking at is what is the probability that I get a heads relative to the probability that I get a tails? Okay? So let's start with a quick example. What is the probability that today, Monday, October 2nd, 2017, is a Monday? It's 100%. Okay? What are some other possible outcomes? Could Monday, October 2nd, 2017 have been a Thursday? Not really. I mean, you could think maybe, but there's a 0% chance it's going to happen. There's a 100% chance. And so in this case, you could frame it in sort of a probability way, but it's really a deterministic example. That probability was either 0 or 1. 0%, 100%. There's not a lot of chance that's going to go on. And so we can contrast that with usually when we're going to use probability terms and ideas, we're going to think about stochastic events, where there's some amount of randomness, there's some amount of chance. And so now, if we were to think about flipping the coin, what are the odds that we're going to observe heads if I flip the coin? You think it's going to be 50-50. What did you assume to make that answer? Well, there's only two sides. That's true, but we made another assumption. It's a fair coin. Anybody seen like a weighted coin? Okay, you can get coins. You can go to like a joke shop and buy ones that are not going to be 50-50. But in principle, you think of a fair coin. It's going to be 50-50. If I flip it, 50% heads, 50% tails. Okay, and that's something more stochastic, because until we actually do the flip, do we know the result? No, if we did, we should go to Vegas, although maybe not yesterday. Okay, so thinking back last time, at the very end of class last Wednesday, we had that pop quiz. And again, just to reiterate, that quiz does not factor into your grade in any way. It was an attendance mechanism meant to inspire an example. And so I gave you a quiz of 10 true-false questions where I clumsily and intentionally neglected to put questions on the quiz, such that you had to guess on all 10 questions. So what's the probability on any one of those questions, what's the probability that you guessed the right answer? On any one question, so I hear 1 out of 2 and I hear 1 out of 10. Which one do you think it is? Well, it's on any one particular question, there's either true or false. You'd probably say it's 50%. Okay? And that's exactly right. So then, if we were to start thinking of those 10 true-false questions on the quiz, how many would you expect to get right by guessing? 5, right? Does anybody doubt that? That seems sort of, you doubt that. Okay. Are you just playing into my hand, or are you, do you? You honestly doubt it a little bit. Good. Okay, well, we'll discuss this a little bit more. But these are some of the questions that this example is trying to get at. And so we can look at that. And so I tabulated your results over the weekend. So I made up an answer key to the quiz, and I graded everyone's thing by it. And you can see that this is basically the distribution we got. I will say no one got a 0 out of 10. No one got a 1 out of 10. There was one person who got a 2. They're a bad guesser. No one got a 10 out of 10, no one got a 9, and one person got an 8 out of 10. That person was a pretty good guesser. But instead we see, there were quite a few 3s, a little bit more 7s, and quite a bit of 4, 5s, and 6s. Okay. So is that to say that, so you took the quiz, and maybe you're the person who got an 8. I don't remember who it was off the top of my head. Does that mean that suddenly, you're really good? No, it means you were lucky. Okay, and I could give the quiz again today, and would that person get an 8 again? Almost certainly not. Could they? Yes, it is entirely a possibility. Would you bet money on it? Not even close. At least I wouldn't. And so part of what we're trying to look at now is, what can we learn from this data? Okay, and what can we see from it? How can we apply probability? What are maybe some other questions that you might want to address here? Okay, so if this had been a real quiz or a real exam or something like that, you're all going to come into the professor and you're going to ask a few questions like, when you get an exam handed back in a different class, what's something you might want to know about the exam over the whole class? Okay, you want to know the answers. Good. Okay, let's do something more quantitative. What was that? Is there a curve? Yes. You want to know what's the average. Okay, how did the average student do? You might want to know what's the standard deviation, how much spread was there? And these are all things that we can start to use probability and statistics to address. Okay? So statistics then comes in and is the idea of interpreting probabilities, where what statistics tries to do, I guess you can define it as the science, and I'll add cynically here in question, it's the art of interpreting probabilities. And in sort of more mathematical context, this is called making inferences, where we have this data, and what can we infer from it? Okay? And so, maybe we won't put that up yet. Coming back again to our greater demons and our lesser angels, what's the background of statistics? Can you think sort of, what was the application that largely developed statistics? Yep. Investing, not even close. That's a great answer. It's a great idea, but investing is way too modern. I mean, people were probably doing it back then, but I don't think it ever crossed anyone's mind to necessarily apply these tools to it because I don't think the stock market was that robust of a thing. Yeah, because you saw it flashed up. Okay, so censuses, going back historically, okay, why were censuses important? Go back like a millennia or 2 millennia. Why was the government interested in having a census? What was that? Okay, so they wanted to know their population. That's fine, but that's not nearly dark enough. They wanted to tax you. And so they needed to know how many people there were to then figure out how much do we put the share around and how much do we extort people for to run the government. Okay. So that's sort of what got statistics going sort of in ancient times. When we actually started formulating these ideas into what we now call statistics, it was actually a very different application. And does anybody want to take a guess what that one was? This goes back about 100 years. 100, 150 in that region. Again, it's something that appeals to our either greater demons or our lesser angels. So the long answer, which is really not that fun, is quality control. Anybody looked at like a process engineering perspective, and how do you know you go to Best Buy and you buy a new TV, how do you know that TV is not going to be a dud? Because Samsung or LG or whoever made the TV has some amount of quality control in their industries to make sure that the assembly line that's putting all these things together is working properly and making good products. Where it ended up coming down, though, so it is in fact quality control, but they were working at controlling the quality of beer. And so we have this guy here. His name is William Seeley Gossett. That's not what he's most commonly known for. He was a mathematician who worked for a pretty well-known brewer in the United Kingdom. Anybody want to take a guess? He didn't set a record for working there. It was Guinness. And he wanted to apply statistics to try to regulate, as they made different batches of the beer, could they make sure that they're getting a uniform and a consistently quality beer out of the processing. And so he started to develop techniques by doing random sampling to say, well, here's this big vat of beer that we're brewing. If we take a small sample, can we determine is that vat going to be a good set of beer or a bad set of beer? Okay, maybe that's hard to quantify, but it can be done. And then from that, they can start to develop better tools to say, well, what are the properties of the hops we have to look for, or of the yeast that we need? What are these different things to guarantee that every time we make a new batch of beer, we're going to get a consistently good batch so that if someone goes to the store and buys a Guinness, they're going to get something that we're proud to sell. And they're not going to get a bad batch of beer and then say, we're never going to buy this again. Now, he's known by a different name. If anyone's taken a statistics course, I guarantee you've heard of his work. But it's not called Gossett's work. Anybody want to take a guess what it might be called? Anyone who's taken a stats course? Anybody heard of the student's t-test? Those that have taken a stats course, okay, people nodding up and down. He's student. Why is it then called student's t-test and not Gossett's t-test? This is a fun story. Yep. They didn't want to put in the fact that he was making beer. No, they're not ashamed of that. This is the United Kingdom. They've got no problem talking about beer. No, it was industrial espionage. So a few years before Gossett did his work at Guinness, the Guinness company had actually had some leakers working for it that went in and started selling the industrial secrets of how Guinness brews its products to competitors. And so Guinness put down very harsh rules on its employees in terms of what they were able to talk about publicly versus what had to stay internal to the company. Basically, it said everything stays internal to the company. And so he develops all of these formulas which had necessarily nothing to do with beer. They were just used to make better quality control by making some of these statistical inferences. And he wanted to publish them for the greater math community. And so he goes to his supervisor, who goes to his supervisor, and so on up the chain to get approval to do this. It took about, I think, 2 years for him to finally get the approval, and even then only under the condition that he publish it under a pseudonym because they didn't want other employees thinking that this was an exception that they would regularly grant. And so they came to the agreement that he could publish it under the name of Student. I don't know how they picked Student. Rather than Gossett, so that other employees wouldn't get jealous that he was getting quote-unquote special treatment. if you're curious. So we've now talked about gambling, taxes, and beer. Like I said, I think we're appealing to our greater demons today. And so some more modern uses for statistics. Okay, obviously, like this, it was sort of developed for those two things, but it's become very prevalent in a lot of applications today. Very recently, if you've seen sort of biometrics or you started looking at bioinformatics, we've started looking at different ways to compare biological data. Can we do like fingerprints or retina scans and determine if I were to go put a retina scan in there, will that match a previous record taken of my retina scan, and will it not match a previous record of your retina? Okay, we can use statistics to quantify that. Bioinformatics, looking at are two gene sequences or two protein sequences alike, or are they different? And how do we start to then understand diversity amongst different people or diversity amongst different species or different organisms entirely? Okay? As we've already talked about, quality control and engineering. How do we know that our industrial process is working correctly and making, I don't know, what do we like to buy today? PlayStation 4. How do we know it's making PlayStation 4s correctly so that you go buy one and it's not going to like turn on and blow up? That would be bad. We'd call it a Motorola, or not Motorola, Samsung Note if it did that. Okay? We can use statistics in meteorology. How do you think the statistics might enter in there? Yep. You're going to say what? Humidity, maybe not so much. Okay, well, how many of you got up and checked the weather forecast before you trudged your way into class today? Okay, and did it tell you that there's like okay, so today it's not actually supposed to rain, but they might say on a different day that there was a 20% chance of rain. Okay, is that sort of probability? Yeah, okay, so there's a certain amount of statistics to go in. Where did that 20% come from? They can run different models and start to infer data from them. Whereas another area, sort of in recent weeks, we were looking at here on Long Island a little bit, but go a little bit south of here, and people were more interested in terms of looking at statistics to try to understand meteorology. The hurricane tracker. So whenever there's a hurricane or this tropical storm working its way across the Atlantic, you can go and see, they say sort of here's the predicted path, and then as time goes on, that cone gets wider and wider and wider. They're using statistics to try to predict what is that storm going to do. And they have various different models to do this, and they sort of average them together in some way. So like when Hurricane Harvey was going into the Gulf and about ready to hit Texas, when they were forecasting, most of the models that sort of average to say it's going to go up and it's going to hit Texas and then sort of curve and go inland to the States. There was one model that said it's going to come back, do like an entire like cane hook, come back, hit Florida, go back out to the Atlantic. And there was another model that said it's going to hit Phoenix. No one was really putting any confidence in those models because they were sort of strays, versus most of the models said Houston's going to get nailed. Or rather a little bit south of Houston on the coast. But there are different models that can go in that can predict this with some amount of probability and some statistics to say, this is what we think that hurricane's going to do. And then certainly a big one this time last year, statistics has now started to become routinely applied to election polling and forecasting. And so this time last year when I was teaching this course, everyone had one thing on their mind. I know this year you were all thinking about the German election that happened over the weekend. And we're looking at how did the polls compare to what happened, and Angela Merkel's party maintained their plurality in the Bundestag. I know you were all thinking that. Okay? But we can apply statistics to try to understand, based on a limited amount of polling data that we have, what do we think is going to happen? Okay? Can you think of other applications for statistics? By no means is this an exhaustive list. Okay, you could look at sports. How so? During like a pitch count, and then you can determine whether or not you want to swing or... Okay, so basically you can moneyball baseball. Okay, where you can look at a different player's statistics and say, well, what are the odds that this pitcher is going to throw this or this hitter is going to hit it? This has led to this whole thing called fantasy sports, where you can start to look at statistics if you really want to moneyball it. I guess you can, but certainly statistics has really come in when looking at different sports teams and forecasts. Yep, absolutely. Okay, so statistics is basically the entire basis of quantum mechanics. As someone who does quantum, I both agree and disagree with that statement, but I don't want to go into that in more detail. Okay? Other thoughts for applications of statistics? Okay, so the idea here is it's very widely applicable. And the idea of statistics, sort of in the broadest sense in my mind, is it's used to determine, it can be used to determine, are two things the same or different? Anytime you want to compare two things, you can use statistics to help understand and quantify the likelihood that two things are either the same or different. Okay? So coming back to those pop quiz results from last time, what do you think? Did those quiz results match what we might have expected? Do you think? Okay, so I see some people sort of like, yeah, a couple people kind of like, no. Okay, well, let's look and see what happens. So what we've got now plotted here, in the blue dots are the data that we actually collected. That's how you performed on the quiz last week. And in orange or yellow, I guess it actually looks sort of like orange on the projector, we've got sort of what we would have expected. I think there were 85 people here last Friday or last Wednesday that took the quiz. So if we just said there are 85 people, it was pure random guessing, what would we have expected to happen? We would get the orange dots. And so you might look at those and say, do they line up? Okay, more or less. I mean, do they exactly line up? No, not really. Notice here that the number of people that got 4, it's actually probably not that far off. 5's not bad either. 7's not bad. The 9 and the 1 aren't that bad, even though we didn't have anyone getting them. But this thing, did we really expect anyone to get a 9 or a 1? Not really. You as the class, though, substantially overperformed on the 6s. A lot more people got 6 out of 10 than we would have expected. But so now the question is, why are there these discrepancies? Are those discrepancies meaningful? Are you as a class better at guessing than the average person? Okay, yes. Fine. You could potentially draw that conclusion from this data. I wouldn't put any money on it. So I am absolutely not recommending you go into your next exam and just guess. Okay? But so why might there be these discrepancies? Yeah.
Because having true or false quizzes a lot, we tend to know there are patterns in questions.
Okay, because you've seen a lot of, you've,
We don't do all true or all false. We don't alternate. We have
right.
a pattern and we default.
Okay, so you've sort of seen, from your experience on taking these types of things, that the answer key will probably not be all true or all false, and so you sort of, vary your answers, and you're thinking, oh, there's probably not 5 questions in a row that have true as the answer. This is one sign, by the way, of never seeing 5 in a row if there's sort of just the 2 choices, that a human just made it up, incidentally. If I were to take out a coin and just start flipping it here and just keep flipping it over and over and over again, you would absolutely see streaks of 5, 6, and 7 in a row. They're not that common, but they're not really uncommon either. So the key for this quiz that I came up with was 1, 2, and 3 were false, and 4 through 10 were true. Makes it easy to grade. And so in that sense, some people got 6s, but there could be those discrepancies because you put in certain patterns, maybe not even consciously thinking about it in your answers. Is it also possible that is 85 necessarily that big of a number? When we were looking at sort of taking all of your data together, is that big enough that we could say we really shouldn't expect deviations from the curve? So if there had only been 2 of you that took the quiz, would we expect to see this nice sort of bell shape in the data? No, because you're going to see exactly either 2 bars that are 1 high or 1 bar that's 2 high. TWO high, not TOO high. Okay? And that's not going to really approximate the bell that well. And so we certainly expect that we need a certain number of quizzes before we're going to start to get the good statistics. And it's possible that 85 just wasn't enough. I can tell you from previous semesters that 200 isn't enough either. Okay? So there could be other sorts of factors. One thing that's led to different discrepancies in the past, and this is sort of an ongoing sociology experiment I conduct in my free time at the glacial pace of once per semester, is to change up what's the combination of results. So like the first time I gave this quiz, it was 5 trues and 5 falses, and actually the bell curve got reproduced pretty nicely. The next time I did it, I gave 7 trues and 3 falses, and the class did noticeably better than guessing, so I think people tend to gravitate towards true answers. And so then the following semester I gave 7 falses and 3 trues, and the results were noticeably worse than random guessing, again supporting that people tend to gravitate towards true answers. So maybe by how I chose the answer key, that influenced the results. Just because, again, there's human nature, and it wasn't purely random guessing. I don't know. And so there's the quote from Mark Twain of lies, damned lies, and statistics. And so sort of one of the points I want to get at here is that statistics cannot, at least not in any application I've seen, tell you why things are different. So we were sort of asking in that last slide, we saw that our quiz results didn't match exactly what we would have expected. They were kind of close, but we asked the question, why were they different? Statistics cannot answer that question. all statistics can do, no, we'll come back to that point in a minute. So, and just as the note here, so statistics can't tell you why things are different or the same. Does that mean people don't try? No, you'll see news reports all the time of, oh, statistics say this is going to happen. No, statistics don't tell you that. And so one of the things that you can get at from looking at statistics is there's this whole website of spuriously correlated things. We'll bring it up in a moment. But you can get fun ones like saying the letters in the winning word of the Scripps National Spelling Bee correlates quite well with the number of people killed by venomous spiders. So naturally, we're going to want to have really short words in the Scripps Spelling Bee, right? Because if that says then fewer people are going to get killed by venomous spiders, that sounds like a good thing. Is there any relationship between these two things whatsoever? Probably not. And so why are they so well correlated? Well, number one, there's just there's a chance. Number two, how many data points are there? There's not a lot. There's 11 data points. If we had maybe 20 data points, do you think this correlation would continue? No. If we had 150 data points, you're probably going to see that they're relatively uncorrelated. And so let's go to this website, because there's some funny things on here. And so you can see, like in this one, U.S. spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. Anyone thinking about grad school might know that that might actually be. Anyway, that was a joke. It was a very morbid joke. Anyway, so you can get number of people who drowned by falling into a pool correlates with films Nicolas Cage appeared in. And it's certainly, if that's now suggesting we need less Nicolas Cage movies, I'm all for it. Per capita cheese consumption with number of people who died by becoming tangled in their bed sheets. I like the divorce rate in Maine correlates with the per capita consumption of margarine. Age of Miss America correlates with murders by steam, hot vapors, and hot objects. I don't know where he gets this data. There's actually this one here. I think this one I'm not entirely sure is unrelated. We've got the total revenue generated by arcades correlates with computer science doctorates in the U.S. That one might actually not be so spurious. But can statistics tell us whether it is or it isn't? Not a chance. Well, the whole point is none of them are supposed to be decent. These are just supposed to be spuriously correlated things. I don't know. Worldwide non-commercial space launches correlates with sociology doctorates. I don't know. Consumption of mozzarella cheese with civil engineering doctorates. Crude oil imports from Norway with drivers killed in collision with railway trains. Anyway, I'm scrolling down here because there's also, you can go in and start to play around. There's a whole bunch of things. Let's look at some. So we've got a whole list of different data sets he's got. Interesting variables, interesting causes of death, miscellaneous. Other causes of death. So as opposed to, these are, I guess, non-interesting causes of death. Death by tripping by gender and state. This guy's pretty morbid here. Anybody want to pick one of these categories? We'll find a variable and see what it correlates with.
Precipitation by state in California.
What was that?
Precipitation by state, especially California.
Okay, precipitation by state in California. Okay, so we can grab California. And we can see that it correlates with, the precipitation in Nevada, the precipitation in Oregon, the precipitation in Idaho and Utah. Okay, are those probably spuriously correlated things? No, those are probably actually correlated. Okay, can statistics tell us that? No, but they probably are. Visitors to Tokyo Disneyland correlates with precipitation in California. That seems probably more spurious. Now, here's one that I think we can all get behind. And so we can actually go and it'll make the chart for us, where the precipitation in California correlates with bicyclists killed in collision with car, pickup truck, or van. And so again, we see that we've got, about 12 different data points. And okay, the correlation's not perfect. I mean, one of them, the blue curve there, certainly fluctuates quite a bit more than the green one. But they correlate about 0.68. So the higher this correlation gets, either to 1 or to -1. 1 meaning they're very well correlated, -1 meaning they're anti-correlated. 0 means they're not correlated. So anti-correlated says as one goes up, the other goes down. So let's actually go back and see what things are anti-correlated with precipitation in California. So we can scroll all the way down to the bottom of the list. There's a lot of things here. Okay, so this one, again, might actually be a real correlation all the way down here at the bottom, where the precipitation in California anti-correlates with visitors to SeaWorld, California, saying that people don't go to SeaWorld when it rains. Okay, that actually may be a real thing. It's anti-correlated with the amount of sunlight in California. Okay. Interesting, it anti-correlates with the visitors to SeaWorld Florida. So when it's raining in California, people don't go to SeaWorld Florida either. Interesting. Here's a fun one. Okay, so the amount of rainfall in California correlates with how much money Pandora loses, or anti-correlates. I would guess this is Pandora, the streaming radio, would be my guess. I don't know. It doesn't say. But the point is they're anti-correlated, whatever the data set is. So, I mean, certainly the link is buried in the lecture notes here. I encourage you to go play around with this, and there's some real fun ones you can discover. But we will sort of move on with our lecture here. Okay, so statistics then, it can't tell us why things are different or the same. What statistics is trying to do is to quantify what is the probability that these things are different or the same. Okay, and so it can't tell us, you know, that these things, again, our Scripps spelling bee word and the number of people killed by venomous spiders, can't tell us that those are really the same thing, but what it can tell us is that they're correlated. There's a certain probability that they're related. In this case, the probability, the correlation might have been, I don't know, let's say it's 0.9. I don't remember exactly what it was for this example. And so what that's trying to tell you is there's a pretty good chance these things are related or that they're the same. Does that mean that they are? Not even close. Because there's still, if there's a 90% chance that things are related, there's still a 10% chance that they're not. And one of the things that we're trying to take away from this lecture is that uncommon things happen all the time. Okay, so we had the data going back. We had that orange data in there that said, how did we expect the class would have done on the quiz? Where did that come from? And so we can start to develop a model where we're now going to bring in a little bit more math here to see where that came from. And so to think about what we know, on that quiz example, we had 10 questions, okay? And any chance of getting one specific question right, or wrong in this case, was 50%. Okay? And so what ends up happening, if we want to use some probability terminology, what we would do is we would say each question is a trial. Okay, and so we're going to conduct each trial now. We're going to have you guess on each question. And we're going to see what's the probability that you got a success. And as we go through all of the trials, how many successes did you observe? So what do we mean by success? Okay, so you guessed the right answer. Could success also have been guessing the wrong answer? Sure. We can define success however we want. The idea that we're going through here is that on any given trial, there are two outcomes. Think of it as, I don't know, in this case, right or wrong, yes and no, up and down, left and right. And we're going to define success as one of the two outcomes, depending on what the question is that we're trying to ask. So if we were asking, how many questions did you get right out of the 10, then a success is probably going to be, I got the correct answer on one particular question. And the other assumption that we're going to have is that all of the trials are what are called independent, which is to say we don't need to know anything about the first trial to understand what's going to happen in the second trial. And was that true on your true-false quiz? Did the answer to number 3 depend on the answer to number 1? No. They're completely independent. I could have reordered the questions, and in principle, nothing would have changed. Okay? So the way that this ends up working, I know there's a lot on the slide, so let's digest this, is the model that we can use is what's called the binomial distribution. And so what this attempts to do is to describe the probability of obtaining this little n number of successes. So we're going to have some big N independent trials. So think like we had 10 trials on our quiz, and little n now says, how many did we get success, or did we get right, if we're going to define getting a question right as a success. Okay? So we can now have the probability that we got 0 of those 10 correct. We can have the probability that we got 1 of the 10 correct, 2 of the 10 correct, all the way up to 9 out of 9 or 10 out of 10 correct. And there's a couple terms that go into being able to calculate this. So let me pull up the marker here. And so those couple terms, so we have this big P sub n, here on thing. This is exactly that probability of observing those little n successes. Did we get 6 questions right? Or did we observe 6 successes out of the 10 trials? This little p as we sort of specify up here, is the success on any one trial. So for our true-false quiz, we say a success is getting the right answer. What's the probability of success? It's 0.5, 50%. Okay? And so what this p sub n term, this little p raised to the n, is that's basically saying, what did we get, how much probability was there to see n successes out of those big N trials? But we also have to go, so that takes care of little n of the trials. What about those other trials? Well, we had to know what's the probability that we got those incorrect, or that we failed on the attempts. And so if the probability of success is p, the probability of failure is 1 minus p. And if we had little n successes, how many failures do we have? Big N minus little n, because there were a total of big N trials minus little n. And so that's where this term comes from. And then the last thing, and this gets a little bit weird, and I don't want to spend too much time on these. I'll give you these or show you how to calculate them. This thing here is sort of in the parentheses with the big N on top and little n on the bottom. It's called a binomial coefficient. It's usually read, in this case, like big N choose little n. It is not a fraction. Do not plug this into your calculators like big N divided by little n. And what this is trying to quantify are the ways to distribute those little n successes amongst the big N trials. So suppose you're going to guess on the quiz, and you get exactly one question right out of the 10. Could that question have been question 1? Yes. Could it have been question 2? Yes. Could it have been question 3? Yes. How many different ways are there to get exactly one question right? There were 10, because we could have just picked any one of the 10. How many ways are there to get 0 questions right? There's only one. You have to get the wrong answer on every question. Where it gets more interesting, how many ways are there to get 2 questions right? Because now you could have question 1 and question 2, question 1 and question 3, 1 and 4, 1 and 5, 2 and 3, 2 and 7, 9 and 10. There's a whole bunch of ways. And that's what this binomial coefficient is counting. What are the number of ways that we can do this? The easy way to calculate this, so on the quiz or something, I would give you these. If you're curious, your calculators can certainly do it. It depends on what calculator you have, how it can do it. But Wolfram Alpha can do it as well. And so we can come over here, and if you type in like 3 choose 1, it'll process. So there's, again, that output showing there's this binomial coefficient, and it tells you there are 3 ways to choose one thing from 3. Again, either choose the first, choose the second, or choose the third. So coming back to some of the examples we had just mentioned a while ago, so we can verify that 10 choose 1 is in fact 10. And if you were curious and you're already starting to think, well, how many ways were there to choose the 2 items amongst 10? We can put that in, and it turns out there are 45. So if you wanted to get 2 questions right, there were 45 different distinct ways you might have done it. Yep, question?
Oh, no.
Okay. So if you wanted to know the exact, you got the 5 right. There were 252 ways on the quiz you could have gotten 5 questions right. Okay. So, like I said, I don't want to dwell on that too long, but we will need some of those numbers. Okay. So, let's clear off the text. Does anybody have any questions about this? We're certainly going to work some examples here. But before we get into that, does anybody have any questions? Okay. So I just bring the formula back here. And so we can now talk about, thinking again about our quiz example, what's the probability that you got exactly 4 correct answers on the quiz? Okay? So why don't I give you maybe about 30 seconds. Think about how you would approach this, or see if you can work something out, and then we'll talk about it together.
Would you call the thing to find the binomial coefficient?
Yep, so that big N choose little n is called a binomial coefficient. And while you work that out, let me go ahead and type into Wolfram Alpha what that will be for this problem. Okay, we get 210. Okay, so to use this formula, we notice there are a couple things we have to determine. We need to know what is big N, which is to say how many trials did we have in our experiment. So what's a trial in this context when we're talking about this quiz? It's the number of questions. So we said there were 10 questions on our quiz. So we know big N is going to be equal to 10. What's little n? Well, little n is the number of successes that we're looking for. What do we want to define as a success? Do we get the question right or do we get the question wrong? Let's say we get the question right. And so we know from the context, we want to know 4 successes. And then little p is the probability of getting a successful outcome on any one trial. And so what's that probability? What's the probability that we got the question right? It's 50% or 0.5. So to get our question here, so we have our p sub 4. And so we're going to have our big N choose little n. So we get 10 choose 4. And we just saw in Wolfram Alpha a moment ago, or maybe I did while you were thinking about this, it's 210. We get 1/2, or 0.5, to the little n is 4, and 1 minus 0.5, big N is 10 minus 4. And so we can now calculate all of this. This ends up being 210. I don't necessarily want to calculate that off the top of my head. Oop, sorry, no 0 point, that's just a 6. You can simplify that up. And that's something we can now put in our calculator and we can evaluate. And it turns out what we end up getting, it's about a little over 20%. So this would actually give us 0.205, which we can then convert to the percent of 20.5. So you had roughly a 1 in 5 chance of getting 4 out of 10 answers correct on the quiz, just by pure guessing. Is that necessarily that unlikely of an outcome? Not really. I wouldn't bet money on it, but it's not fleetingly rare. People win the lottery most times it's run, and I guarantee you the odds are a lot smaller than that. Certainly everyone doesn't win the lottery, but a lot of people do. Or there's at least that one person that does. Excuse me. Okay. And so we can come in and we can now maybe ask a different question that sometimes students like to ask. What is the probability of getting at least 8 correct answers? Okay, so how do you think we could approach this problem? Take a minute and think about it. Okay, so how would you approach this problem? Can we use the formula we've got up top here as is, or do we have to do a few things first? Okay, so we're going to have to look up the binomial coefficients, but I think we need to do a few, yes, you're right, we're going to need to do a few things before that, though. Again, whenever we're thinking about these binomial distributions or these questions, we need to start with a few things by asking how many trials are there, how many successes are we looking for, and what's the probability of success on any one trial. And so in this case, how many trials are there? There's still 10. We're talking about the same quiz. How many successes, okay, so we'll keep our convention that a success means you guessed correctly. How many successes are we looking for? 8 or 9 or 10. Any one of those 3 outcomes would satisfy this, because we said now it's not the probability that we get 8 correct, it's that we get at least 8 correct. So we actually have to calculate 3 of these things, because we're going to need our p sub 8, p sub 9, and p sub 10. And so if p sub 8 is the probability of getting exactly 8 correct, and p sub 9 is the probability of getting exactly 9, and p sub 10 is the probability of exactly 10, what do we want to do to those 3 numbers to get our final result? We just add them together. Okay, so in the interest of space, I'm going to switch over to the whiteboard thing, and we'll copy this stuff over, and we'll work this out. And just ignore the answer that you see there of 5.5%. There it is. Okay, so we had, from our slide, that p sub n was equal to n choose n, little p to the little n, 1 minus p to the big N minus little n. Okay, and so we saw just a moment ago that what we needed was P8 plus P9 plus P10. So P sub 8, we can do it just like we did on the previous example for looking at 4 correct answers. We can get our binomial coefficients, so we'll have our 10 choose 8. How many ways can we get 8 correct answers out of the 10 questions? 50% chance for a right answer with 8 right answers. In this case, 50% chance for wrong answer with 2 wrong answers. I'll field you that the binomial coefficient in this case is 45. Again, you can put that under Wolfram Alpha to verify. And when we calculate all of this out, I actually don't have the final result here. It's going to be 45 over 1024. I don't know what that is in decimals. That's going to be loosely 0.004, 0.005, somewhere in that region. So is that a very likely, sorry, 0.04 or 0.05? So it's about a 4 to 5% chance. Again, is that now a very likely outcome? Not really, but again, not necessarily that uncommon. Remember, we actually saw there was one person who did get 8 correct on the quiz from last week. So we can do the same thing for P sub 9, just changing out all of the 8s for 9s. And then that 2 becomes a 1 because it's 10 minus 9. How many different ways are there to get 9 correct answers from 10 questions? There's 10. Because we can choose any one of the 10 to be the wrong one and go. So we'll field that. This ends up coming out to be 10 over 1024. And then last P10, 10 choose 10. How many different ways are there to get 10 correct answers out of 10 questions? Exactly 1. 0.5 to the 10 for those. 0.5, clean that up. 0.5 to the 0 for those. So we get 1024. You add all this together and put it into decimal form, and what you get is about 5.5%. Okay? So if you asked what was the probability that you got 8, 9, or 10 answers correct, it's a little over 5%, about 1 in 20. Okay? So again, maybe not great odds, but not astronomical. Again, I wouldn't necessarily have bet if you were any one student, I wouldn't bet that you get an 8, 9, or a 10. But as we saw, someone did.
When you do select homework and stuff, do you want to round up like the nearest 10?
Usually select for homework, usually tenths, maybe hundredths. I usually give the solutions to, I think, 3 digits. Okay, so that's how we can actually calculate those probabilities. Another useful statistic that we might want to look at, okay, is this idea of the expected value or the mean value. And so the question we might have wanted to ask this is, how many questions do you expect to get by guessing, expect to get correct by guessing on your quiz? And we already know the answer for our quiz was 5. Where did that come from? If we're using, again, this binomial distribution, the average value or the expected value or the mean value, these are all equivalent terms, is just big N times little p. Take what is the number of trials you have, so we had 10 questions for our 10 trials, and multiply by the probability of success in any one trial, 50% for our true-false quiz. 10 times 50% is 5. And so you would expect that by randomly guessing, you would have gotten 5 of those 10 questions correct. Does that make sense? So we can vary it up a little bit and have some examples. So you now have 20 questions on a quiz, and you have to guess on all of them. If there are only 2 options, so either it's true, false, or just a 2-option multiple choice test, how many questions do you expect to get right? 10. Because we now have how many trials? 20. And what's the probability that we get any one of them correct? Still 50%, 1 out of 2. 20 times 0.5 is 10. What if we had 4 options? So now there's A, B, C, and D, multiple choice answers. How many questions do you expect to get right by pure guessing? 5. We still have our 20 questions, but what's the probability that we get a question right? It's now 25%. 5 times a quarter is, or sorry, 20 times a quarter is 5. Okay? So again, you've already got a pretty good idea of what's going on with this. Just think about it in terms of questions on a multiple choice quiz. Okay? So, cautionary note on expected values, just for broader context. The expected value that you actually calculate doesn't have to be a possible outcome. So for instance, suppose we had a 9-question true-false quiz. How many questions do you expect to get correct? You would expect to get 4.5, because there are 9 questions times the 50% on each question. But is it actually possible for you to get 4.5 questions correct? No. So this is saying you're probably going to be equally split between a 4 and a 5 in this case. But just again, keep that in mind. Expected value doesn't have to be an actual outcome. Okay? And so this is where what happens for the expected value is that you would expect to then start to approach this number as you perform the experiment lots and lots and lots of times. So suppose now for our quiz, I give you the 10-question quiz, and I give it to everyone in the class, much like I did. And we come back today, and I give it to all of you again. And I come back on Wednesday and give it to all of you again. And we start getting more and more and more and more and more. And we look at what's the class average over all of these quizzes. We would expect that as more and more and more and more and more of these quizzes are given, tabulated, and added in, that the average person would get how many questions right? The class average would approach 5. Because there were the 10 questions at 50% per shot. We would expect to see that. This is what's called the law of large numbers. For those that have taken a statistics course, it's also known as the central limit theorem, but I don't want to go into that. And so what this is saying is when you think about this expected value, this is what's going to tell you if you run this experiment with however many trials you set, whatever the probabilities were, as you run that entire thing over and over and over and start to aggregate all of this data, this is the result that you would expect to see once you've got a really large number. So suppose now the enrollment in this class was very high. We had 1,000 people enrolled. I gave this quiz out, and on average, the class average was a 3.5 out of 10 on the quiz. What do you think? Does that reflect that random guessing is happening? Probably not, because if it were purely random guessing, at that point with 1,000 quizzes, you would expect that that average value is pretty close to 5. Okay? If there were only 2 quizzes, so suppose I only give the quiz to 2 of you, and we got the average value between 2. So one of you got, I don't know, a 1, and one of you got a 4, which averages to a 2.5 out of 10. Does that necessarily indicate that there wasn't random guessing? No, there's only 2 outcomes. The fact that one of you got a 1 and one of you got a 4, while maybe not the most likely of outcomes, is that really strikingly weird? Not really. And so this then gives, on the other hand, the law of small numbers, which says that if you have a small number of total samples or total experiments, anything can happen. And this is exactly what happens with the lotto ticket. So you buy 1 lottery ticket tonight. I have no idea if there's actually a drawing later this evening or not. And you happen to win. Okay? You only bought 1 lottery ticket. Is that weird? Is that to say that you're just naturally a winner and you should just buy lottery tickets every day? I don't know, because probably not. As you buy more and more lottery tickets, let's say you buy one every day for the next year or 2 years, that's what, 700 some tickets? How many of them do you expect are total winners? Probably less than 1. The fact that you got that one the first day, good for you. But you wouldn't expect that trend to continue as you buy more and more and more lottery tickets. And this is where sort of that spurious correlation ends up coming in. So again, notice when we had our example of Nicholas, well, this is a different example of films Nicolas Cage appeared in with female editors on the Harvard Law Review, shows they correlate pretty well, which now is a good argument for saying we need more Nicolas Cage films. But on the other hand, does anybody believe putting Nicolas Cage in more films is going to lead to more female editors of the Harvard Law Review? No. How many data points did we actually have here? 5. Law of small numbers. Should you infer anything about correlation between 5 data points? No. That's just not enough information to do anything useful. Now, if this trend had persisted over 1,000 data points, now maybe you're looking and thinking we need to get Nicolas Cage in more movies. And hopefully that day never comes. Okay, so for sort of the little joke here, you know, I used to think correlation implied causation. So correlation saying the data is correlated like what we just saw, but it's not a causal relationship. We don't think Nicolas Cage actually caused there to be more female Law Review editors, just as much as saying more women at Harvard Law Review on that didn't result in more Nicolas Cage films. They're unrelated. So I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Because the class helping would be a causal relation. Anyway, don't ever confuse correlation with causation. Statistics can only tell you correlation. It can't tell you causation. And when people try to tell you statistics is saying causation, tell them they're full of something. Okay, so let's tie all of this back. We spent a bunch of time looking at this binomial distribution and thinking about our true-false quiz. So now you see why we motivated that last time. Let's bring this back to the data transmission. So why did we have this foray? Well, the reason being, and I know I'm sort of reading from the slide here, under some convenient assumptions, this idea of data transmission can be viewed as a probability problem where we're going to use the binomial distribution to try to quantify. And so when we come back to our driving question, how do we know or guarantee that the message received is identical to the message sent? What we can try to use this probability for is to quantify how many errors do we expect to see in the message that we send. And we can quantify that using this probability in statistics. Okay? So we come back to our previous example, and some of you asked some questions about this after class last time, where we're sending our photo on a text message to our BFF. And our photo is 3 megabytes, and we have a really spectacularly good channel that correctly transmits each bit 99.99% of the time. So we asked, what were the chances that your friend, your BFF, gets the correct image? And we found that it was 10 to the minus 1,093. Where did that number come from? Okay, so what it turns out is we can start to think about this example now as a binomial distribution problem. So we need to figure out how many trials do we have? Well, what's a trial, do you think? Yep. Did each bit get transmitted correctly? Okay, so if that's the case, so we need to now look and say, well, the total number of trials involved is the total number of bits. Okay, so if we want to put this in, so we could have our big N, number of bits. Well, unfortunately, we were given that file in megabytes. Okay, so we've got to convert our megabytes to bits. And so we have 3 megabytes. Going back to our powers of 2, we know that mega is the prefix for a million, but we're going to use the 1024 instead of 1,000 because it's a power. We're talking about bits and all that. And then what's the relationship, thinking back about a week to 2 weeks ago, between a bit and a byte? There are 8 bits in a byte. So we have to multiply this again by 8 to get the bytes back for bits. And when we carry this through, what we end up getting is that there are 25,165,824 bits in that image file. Okay, so that's a lot of bits. We've got a lot of trials we've got to work with here. And remember, to get the picture correctly transmitted, we need every single one of them to be a success. Okay, so now, coming forward again, how many successes do we then want for our little n? We have these 25 odd million trials. How many do we want to be successful? We want all of them. 25,165,824. And what is our probability that any one trial is successful? Not quite. That's the trial that the entire thing works, or the probability that the entire thing is successful. What's the probability that any one bit is successfully transmitted? 0.9999. So we can say, well, now we want our success to be the bit is transmitted correctly, such that we need the 25 million successes, and the probability of any one success is 0.9999. So how many ways are there to get 25 odd million successes from 25 odd million attempts? 1. We have to get them all right. Okay, so our P sub, and I'm just going to do 25 million, is equal to 25 million, choose 25 million, which just happens to be 1, 0.9999 to our 25 million. And then our remainder, the probability of failure, is 0.0001. And how many of those failures do we actually have in this example? None. So we raise that to the 0 power. And so this is just 1. This term is just 1. And so the probability now is this 0.9999 to the 25,165,824, even though there's only that very small chance that any one bit gets transmitted incorrectly. When we look over all of the bits we have to do, that starts to add up. Okay? And so the total probability then that we see absolutely no misses is incredibly small. You can evaluate that 0.9999 to the 25 million. If you try to do it on your scientific or graphic calculator, it's probably just going to come back and say 0. That is such a small number that your calculator can't store it in the limited amount of memory it has to process numbers. What was that? Right, so think back to the data storage unit. We would need more bits. You need a more powerful calculator to be able to see that number. Okay? So does that make sense where that number came from? A little bit? Okay. So we'll clear this off and we'll ask maybe a related question. Again, working with our binomial distribution here for probabilities. Okay, so there's the work, exactly what we had. Suppose we can make our channel more accurate. So think about this now from an engineering perspective. We're willing to accept that there's only a 10% chance that our picture gets transmitted, the entire picture gets transmitted correctly. So we might have to send that picture maybe 10 times to get it through. What is now the lowest probability that we can handle for dealing with to say what's the probability per bit? So we had 0.9999 up above. What is the lowest probability that we can tolerate to make this the case? From an engineering perspective, how good do we have to make our channel such that we know there's a 10% chance that this photo is going to get through correctly? I'll tell you, it's got to be pretty darn good. But we can come over and we can look at this real quick. And so again, we can use our binomial distribution. So we'll have our p sub n, sorry, that should be a little n, is equal to our big N choose little n, p to the little n, 1 minus p to the big N minus little n. And so now what we're given in that problem, so we were told we wanted a 10% probability of something. What was that probability? So it's the probability that our entire image gets transmitted correctly. What symbol would that be? What quantity are we trying to describe here now for this binomial distribution? That's p sub big N. Okay? So remember, p sub big N is the probability that all bits get transmitted correctly. And we said we wanted this to be a 10% chance, that our image gets through in its entirety. Okay? And we know then from this that little n has to be equal to that, what was it, 25,165,824, and that our big N, we're still working with this 3 megabyte picture, is still 25,165,824. And so what we were looking for was what was the best probability per bit of getting a successful transmission. And so we're looking for now our little p. What is that probability? Well, just as we saw, the big N choose big N for our binomial coefficient. Again, we're looking for all bits to be transmitted correctly. How many ways are there to do that? Just the one. So that goes to 1. This 1 minus p term for the failures, what's big N minus little n? It's just 0. So anything to the 0 is 1. And so what we're now getting is that 0.1 is equal to p to the 25,165,824. We can raise both of these sides to the 1 over 25,165,824 to get it. And does anybody have a feeling what 0.1 to that number is going to be? Who thinks it's pretty close to 1? As I say, you've got to have basically a 100% probability of this happening. It turns out it's incredibly close to 1. This is, again, another one of those, if you try to put this number into your calculator, it's going to come back and just tell you 1, because your calculator doesn't have enough digits, enough memory in it, to actually compute what the number is. In a previous semester, I went and looked, and I think even to 1,000 decimal places, it's still 0.99999999999 going out 1,000 digits. So the point is, even from this engineering perspective where you say, okay, well, we're willing to suffer a 10% problem, we've still got to have a very accurate channel to make that work. Okay? So now, asking sort of an expected value problem, let's simplify things and make these numbers maybe a little bit more manageable. Suppose we only want to send 7 bits. Okay, so this would be a really bad image file. Really horrible resolution. Okay? There's a 75% chance that each bit gets transmitted correctly. And so you could ask yourself, now, what is the probability your friend receives the message with exactly 1 error? Is this something we can now address? Yeah, we can bring in our binomial distribution. How many trials do we have? So first of all, what's a trial? A bit, we're going to send a bit through the channel. That's a trial. So how many trials do we have? We've got 7 trials. What do we want to define as a success here? Okay, the number, did the bit get transmitted with an error? We can do it either way, but sure, we can take that tack. So now a success from the binomial distribution perspective is our bit got transmitted wrongly, incorrectly. So how many successes do we want? Well, how many errors are we looking for? We're looking for 1. So we want 1 success. And what's the probability of success? It's not 75%. It's 25%, because here now, 75% is the chance that each bit gets transmitted correctly, but we defined a success to be the chance that it gets incorrectly transmitted, which is a 25% probability. So to put that all together, the way we could do this is now our big N was equal to 7. Those were our trials. The number of successes we wanted was 1, and I'll put parenthetically here, that was errors. And then our probability of success was 0.25, again, because we chose success to be errors. Could we have chosen the success to be bits are transmitted correctly? Yeah, we could. And you could rework it out. Little n would then be 6, and little p would then be 75%. You'll get the same number. Okay? So what we're looking for, just briefly, is p sub 1, which we're going to get 7, choose 1, 0.25 to the 1, 0.75 to the 6. And when we put all that together, we end up getting about 31% if you evaluate that through. Okay? So let me clear this off. We'll bring up that answer just to make sure we got that right. We did.
So, Pete, so binomial coefficient, the 7, 1, would that be 7?
It would be 7 again, because how many ways are there to have that 1 success amongst 7 items? We'll just pick. It's either item 1 or item 2 or item 3. Yep. Okay. And so to just wrap things up for today with where we're headed, so what we saw there, where we only had the 7 bits, there was a much higher probability that the message got through because the message was shorter. Even if our channel has some problems, if there's just less bits to send through, we're going to expect fewer errors. We're going to see fewer errors. And so maybe what we can do is we can chop our message up. And so even if we have those 25 million bits, if we send through a lot of smaller messages that might have 7 bits or 10 bits or even maybe 100 bits, there's much less chance that things are going to go wrong. Yep?
Is that kind of like when you try to send an email from your phone, when you try to send a picture, it says like you want to send it in smaller bit, you want to send it in smaller.
Right, so this is why your phone might ask you, do you want to send a lower resolution, because then it's a smaller number of bits, easier to get through. And so now there are fewer bits to garble, so we get less errors. If we discover an error, it's potentially easier to correct because we know it had to be in this chunk of however many bits we sent. And so this idea of breaking things up, we're going to see it again when we come back to the internet unit at the end of the semester, is the same idea as packets. And so where we're now going is how can we think about trying to detect and or correct errors in now maybe these smaller messages that we're going to break up and send through. And that will be the focus of our discussion on Wednesday. Thank you for your attention. Remember, we have a quiz on Wednesday, and I will see you then.